today's program, we will be talking about transportation. We will see how efficient management of railway and airline networks can reduce problems of congestion. We will also learn about how tunnels are built. In the old days, a deluxe railway coach looked like palatial living rooms, complete with chandeliers, golden woodwork, and velvet curtains. The passengers who traveled to Constantinople aboard Orient Express opted for romanticism. They were delighted that the trip lasted several days. Today, the objective is to reach the destination as quickly as possible. The greater the number of trains and the faster they are, well, the more impeccable the organization of railway systems has to be. Since the first steam locomotives, the use of trains has grown by leaps and bounds. Today, vast railway networks ensure the distribution of merchandise, the transportation of countless passengers, and they do this almost as fast as airplanes. However, the more we rely on trains, the more complex railway traffic control becomes. As a result, sophisticated systems are needed to manage these railway networks. The movement of trains is coordinated by a pre-established computer program. The software is designed to prevent slow-moving trains from interfering with fast-moving ones. The program also eliminates unnecessary stops, keeping only those absolutely necessary. Changes in a train's direction are done by switches. In the old days, all the switches were hand-thrown with levers and rods. They were later replaced by electrically operated switches, which are now also on their way out. Increasingly, track switches are being controlled electronically from a switch stand. Using a large visual board, a technician can monitor all train positions and assess the traffic conditions. When a train nears a switch stand, a single command from the operator is enough to set all the switches so it can continue on its way. Every station has its own switch stand of varying importance, depending upon the amount of railway traffic in the area. A central control station coordinates the activities of a sector's switch stands and makes sure the trains run smoothly and on schedule. On high-speed lines, control stations are enhanced with switch remote controls. These remote controls, activated manually or by computer, lock all the switches into a position that will take a train to its station of arrival. A simple and sure signal system, called the automatic block system, ensures train safety. Every railway line equipped with this system is broken down into roughly 1.5 kilometer-long segments called blocks. The blocks are marked by signal lights placed on either side of the track. Automatic block systems work by means of a weak electrical current that runs through the two rails in every block. When a train enters a block, its axles and wheels, which conduct electricity, cause the electric circuit formed by that block to close off. The short circuit turns on a red signal light at the block's entrance. That signal remains on until the train leaves the block. The signal obliges any other train to stop, thereby preventing a collision. However, since a heavy train requires a fairly long distance to be able to stop safely, the conductor is forewarned by an advance stop signal. When the train moves into another block, the signal installed at the beginning of the block it has just left turns yellow. This warning signal orders the conductor of the next train to slow down. The signal at the beginning of the first block only turns green when the first train has started into the third block. This all-clear signal tells the conductor in the following train that he can go on or resume his normal speed. Since there is always one block between trains, one train can never catch up to another. The signal system is constantly being improved. For example, on high-speed trains, it would be difficult to read the signals set up along the track. Trains are now equipped with sensors that monitor the presence or the absence of frequencies in the tracks. The information they pick up is relayed to the train's control stand, where it is displayed on indicator signals. These safety measures are very effective, but researchers are working at improving them even more. A system currently under study consists of placing a set of instruments on board trains that would pinpoint the train's exact position and relay the information to a traffic control office. Such systems are made up of electronic transponders placed along the track at regular intervals. When a train passes one of these transponders, a sensing device concealed under the lead car reads various data, including the train's exact position. A microprocessor decodes the data, which is then either relayed by radio or even satellite to the control center computers. The control center analyzes the data and sends it on to all moving trains in the area. This way, they are all aware of the position, velocity, and composition of all the other trains in the network at any given moment. Track signals are no longer necessary. Each train is therefore enclosed in a sort of safety bubble that protects it from collision. All this information will help to improve railway traffic management by selecting the best routing and crossing order for all trains. Even though trains are currently the safest means of transportation, research continues to try and make them even safer and more efficient. Because it transports a large number of passengers at the same time, the train could be considered less polluting than road transportation. Another factor that plays in favor of its popularity is the congestion of the other transportation networks. Today, in all industrialized nations, the airline system has reached the saturation point. Planes circle over airports in single file, waiting for the authorization to land. But whereas the passengers have thoughts of business, getting away from it all, and rest dancing in their heads, down there on the ground, people in the control tower are managing the traffic and dealing with stress. During the last 50 years, the amazing development of commercial aviation has turned the sky into a gigantic network of expressways. Managing this ever-growing air traffic and preventing air accidents is now the responsibility of air traffic control. Every flight is taken on by a coordinated team of specialized technicians called air traffic controllers, who rely on leading-edge technology. Before departure, the pilot first prepares a flight plan. The flight plan includes such data as the identification and type of aircraft, its origin, route, and destination, as well as the expected duration and altitude of the flight. The flight plan is relayed to ground computers, where it is processed and stored in memory until takeoff. Just before takeoff, the pilot radios the control tower. He talks with the controller, whose job it is to call up the flight plan on the computer. The flight plan is then transcribed onto a strip of paper known as the flight progress tape. The flight progress tape is constantly updated during the flight. The control tower then guides the plane toward its takeoff runway, while informing the pilot of prevailing weather conditions. It then tells the pilot to taxi onto the runway and gives him permission to take off. Tower controllers monitor all takeoffs, landings, and other flights in the vicinity of the airport and ensure that all aircraft keep away from each other. Should two planes get too close to each other, the controllers give them an avoidance maneuver, such as a different heading or altitude, thus preventing a collision. Besides detecting the planes by radar, Tower controllers can monitor landings and takeoffs visually. Once a plane has taken off, its guidance is no longer handled by the control tower, but by an area called the Final Approach Control Room. The Final Approach controllers direct the aircraft towards their air route. However, once a plane is airborne, radar keeps track of its progress. Radar consists of a constantly rotating transmitting antenna and receiving antenna. The transmitting antenna emits an electromagnetic wave that sweeps over the sky. Electromagnetic waves are partially reflected by metal objects, and this is what makes radar work. For example, when waves from the transmitting antenna meet with a plane, they are deflected and picked up by the receiving antenna. The reflected waves provide various information on the positions of the aircraft in the sky. In the air traffic control rooms, the data appears on circular cathode screens, each plane being represented by a dot of light. The plane's distance corresponds to the distance between the dot of light that represents it and the center of the screen. The plane's direction is given by the position of the dot of light around the center of the screen. Besides this primary radar, secondary radar is now being used. This radar system consists of a device called a radar transponder, which is installed aboard the aircraft. When a radar transponder picks up waves from a ground radar, it in turn emits coded data, including the identification of the aircraft and its altitude. This information is also displayed on the controller's radar screens. It enables the controllers to identify the various planes. When the aircraft has reached its cruising altitude and speed, the en route control center takes over. The en route controllers see that the plane stays within its assigned corridor for its entire journey. They also make sure that when one plane is following another, they keep far enough apart. The most difficult stage in air traffic control is the landing. Indeed, no runway can handle more than one aircraft landing about every 2 minutes. When incoming aircraft exceed the runway's capability, the controller has to detour them to waiting circuits, where they circle awaiting their turn to land. The controllers ensure there is always sufficient space between the circling planes, correcting their speeds and altitudes when necessary. When they land, the control tower stays in touch with them until they make a full stop at their gate. This is done by a controller who has a direct view of the gate area. He is in constant radio communication with all vehicles moving in the maneuvering area. A specific radar also allows him to see all ground vehicle and aircraft movement. Air traffic control is constantly being upgraded to increase flight safety and facilitate the work of air traffic controllers. According to statistics, traveling a kilometer in a plane is 15 times safer than in a car. One day, air traffic control will be done by satellite. Radar only covers a limited area. Satellites can handle much greater territories and ensure coordination on a planetary scale. Today, satellites have become the answers to many problems. Did you know that it was a satellite that monitored the progress of the 2 tunnel arms built to converge under the channel, linking France and England? Since the world is covered with natural barriers, the construction of tunnels has often seemed an elegant solution to getting around such obstacles. Is the straight line not the shortest route between 2 points? But the construction of a tunnel is no mean affair. It requires considerable technical means. The construction of a tunnel begins with a geological profile of the terrain. The profile reveals the various layers of rock. Among them, the one presenting the best qualities, such as airtightness and hardness of the rock, is selected. In most cases, tunnels are dug by dynamiting. However, the work gets done much faster with drilling machines called tunnel boring machines, or tunnelers. Veritable mobile factories, tunnelers can complete virtually all the stages of a tunnel's construction. They dig, evacuate the rubble, and set cement tunnel lining. A tunneler is an enormous cylindrical machine, slightly larger in diameter than that of the tunnel. It bores into the rock with a rotating shield, called the cutting head. The cutting head is controlled by an operator seated inside the tunneler and is fueled by powerful electric engines. It holds toothed and cutting wheels made of tungsten carbide, an extremely hard, abrasion-resistant compound. The toothed cutting blades chew into the rock. The rubble is evacuated with an endless screw, or Archimedes' screw. The rubble is then sent on a conveyor belt to small trucks to be taken outside. To advance through the ground, the tunneler has to exert considerable thrust against the rock surface. It does so with powerful hydraulic pumps that take leverage on the lining it has already set down. The pumps push the tunneler ahead with a force equal to several thousand tons. A tunneler can advance this way a few dozen meters per day. However, it does more than drill the tunnels and extract the debris. It also installs the prefabricated elements that make up the tunnel's lining. That lining provides the tunnel with durability and airtightness. It is composed of a series of rings of reinforced concrete. The rings are made up of elements called voussoirs. The prefabricated voussoirs are installed by the tunnelers as they move ahead with erector arms. The erector arms start by installing the voussoirs located at the ring's base. They then install a final voussoir at the top of the tunnel. Veritable keystone, this beveled voussoir ensures the stability of the whole. To further increase solidity and airtightness, mortar is poured between the surface of the lining and the rock. Each tunneler is adapted to the kinds of conditions it is likely to encounter during the drilling. For example, under an arm of sea, water may filter in if the rock layer chosen for the drilling is not homogeneous. Tunnelers likely to go through water leaks have to be completely watertight. They can accomplish this thanks to techniques that completely insulate the machine from the surrounding terrain. Fitted like a submarine, the tunneler continues to advance. A pumping system evacuates the rubble in the form of a liquid mud. However, progress is much slower than in dry ground. A very precise guidance system is used to make sure the tunneler does not stray from its path. The guidance system consists of a laser source placed at a certain distance behind the tunneler's cutting head. The source sends a laser beam onto two targets placed 3 centimeters apart on the tunneler. A microcomputer displays the direction planned and the direction followed so that corrections can be made if necessary. The final installations are done by a technical train that can be 250 meters long. The train, which is attached to the tunneler and slides along rails it sets down itself, installs the ventilation, lighting, and electrical systems as the tunneler advances. Tunnelers have to be dismantled once they've completed their work. Indeed, tunnelers cannot go in reverse, since the tunnel behind them, with its lining, is too narrow. While highly complex, the construction of a tunnel is only one step in the setting up of a new line of communication between two geographical areas. For instance, a major road and railway network may be necessary to access the tunnel to as many vehicles or trains as possible. However, once everything is in place, a tunnel may well become the vital link in a region's or even a country's transportation system. Man has been interested in tunnels for a long time. The ruins of a tunnel dug 4,000 years ago in Mesopotamia were discovered under the Euphrates riverbed. Technology and the sites may have changed, but the challenge today is as daunting as that of yesteryear.